So this is going to be a talk about logic and learning. I'm going to start with this quote from Aristotle, which is in some sense the definition of logic. So what Aristotle is saying here, and this is the source text of logic, the Sophistical Refutations, is that logic is about the distinction between arguments that are correct and incorrect. But you can see that by analogy Aristotle is drawing on the idea of perception as the basis of logic, right? The idea that distinguishing between correct and incorrect deductions is something like distinguishing between a case where our senses are fooled and where our senses are not fooled. So Aristotle is clearly the birth, that essay, text, is clearly the birth of logic. And maybe the second dawn of logic was Boole's work in 1854. So he wrote a book called An Investigation of the Laws of Thought. Now that's where we get the idea of Boolean algebra and truth tables and so on, which you've all learned. But this book is well worth reading because it's actually much more interesting than what you would have learned as an undergrad about Boolean algebra. So what Boole was trying to do in this book was to uncover the fundamental laws of the operations of the mind, which we call reason, and to encapsulate those laws in symbolic language, in a calculus that could be used to emulate those laws of thought and to perform those operations of thought and reason more reliably. And that's what he sought to found the science of logic on, that calculus and those laws. Okay, so I would argue that we're in the process of experiencing something like the third dawn of reason or logic, which is in a very different form and largely in machines. Okay, so I'm back over on the third board here, and I'll just start writing. Okay, so that's the subject of my talk today, which is what I'm going to call the third dawn of reason. And this, takes many forms, but maybe I'll highlight three important landmarks in what's been happening in the last decade or so. So Alphago, Alpha Star, and AlphaFold very recently. So I think most of you have heard of Alphago. So that's a deep learning based system, reinforcement learning based system that plays Go and then also several other perfect information board games. The system is based on convolutional neural networks, which are a kind of perception based on loosely the way that the human visual system works, but also tree search, which is an older idea in the automated study of how to play games. So it's perhaps controversial to refer to any of these systems as reasoning, but particularly perhaps the first one. So just because a system can play Go very well doesn't necessarily mean that it's performing reason in any sense. And the fact that AlphaGo had built into it this tree search component, which you could say was a very strong input from the human designers about how you should think about games, means that it's perhaps not absolutely clear that you should think about AlphaGo as reasoning. And similarly, the fact that the system is based on convolutional networks means that essentially what AlphaGo is learning to do is to see the board in a very profound way. So there perhaps isn't a very deep distinction between perception and reason. So that's an idea that's quite current in the neuroscience literature, for example. But I think we have to look to these later examples to find ingredients in the design of the neural networks which makes it basically untenable to believe any longer that these systems are not doing some kind of reason. So I'll make that argument as we go along, and that's based on the presence of what are called transformer networks. So alpha star and alpha fold, they're both quite complicated systems. So they're not very simple neural networks. They're made of many components, each of which have a lot of thought put into them. But in both cases, a fundamental component is what's called a transformer. And I'll tell you what that is. So a transformer is a particular kind of neural network, which you can think of as computing with learned representations via geometric algebra. And that's the entry of mathematics into this talk. Okay, so Alpha Star is a system that plays also deep reinforcement learning based. It plays StarCraft 2, a real-time strategy game, in which obviously Zerg is the only decent race, and AlphaFold, which is about protein folding. Okay. Okay, so I'm going to rotate around back to the first board here now. So I just want to make a comment about Boole's work before we get into the details of what a transformer is, so the analogy becomes perhaps more obvious. So in Boole's work, a proposition P about the world is an element of an algebra. And the way he thought about these propositions as elements of an algebra is that they were operators on some hypothetical state which project onto configurations of the world satisfying the proposition P. Now, as you're familiar with, conjunction of propositions is the multiplication in this algebra. Now, in transformers, as you'll see, a relationship between entities is represented by what's called a head. And a head is a function which takes entities, sort of semantically meaningful things like units in StarCraft or amino acid residues in a protein, and maps them to vectors in some inner product space. And what I'll explain is that you can think about multiplying any two vectors in an inner product space using Clifford algebras. Okay, and that's maybe the connection between Boole's point of view on how to think about logic in terms of algebra and what has ended up being the most successful by far architecture in the history of machine learning, which is transformers. Okay, so let me define transformers. So, moving on again. Feel free to interrupt the questions, obviously. Okay, so what's a transformer? Well, it's a neural network It operates on a set of entities. Let's say E1 through En, which I'm going to identify with vectors in some vector space V. It operates on these vectors by first learning to embed them into an inner product space. So the operations use learned transformations. Phi q and phi k. I'll explain what q and k stand for in a moment. Now these are learned, so these linear transformations are determined by a bunch of parameters, and those are varied by gradient descent given some loss function in order to make this system learn how to operate on these entities, where H is an inner product space. Okay, so given an entity, the output of phi q on that entity is called a query. For entity I, and the output of phi k is called the key. All right, so what the point of learning these queries and keys is that the transformer represents the inductive bias that a relationship exists between entities I and j I'll just write ij rather than ei, ej. And unlike formal logic, it's not a true or false thing. So a relationship of, say, this entity is the father of that entity isn't represented as either 0 or 1, but rather something like a probability. So it's a scalar value. And it's given by, so that relationship is believed to exist by the transformer, so to speak, to the extent that the dot product, or pairing, qi, kj, is large and positive. Okay, so this is, it's a very simple idea. To associate two entities, queries and keys, and believe in relationships between them to the extent that some two vectors have a certain configuration in space. Okay, so let me give you a few sort of kind of examples to think about this. So back over here. Okay, so let me use green to stand for queries and blue to stand for keys. And let's suppose there's three entities in the world. So entity J, entity I, and entity K. Now suppose the learned transformations phi q and phi k send our entities to the following arrows. So let's suppose the query for I looks something like this. For J looks something like that. For K like that. And the keys similarly look like this. Okay, so the information in these vectors is both the angle and the length. I'll come back to the length in a moment. You might like to think about what that could possibly mean. So maybe I'll write out the formulas. Let's see, can I fit that on here? Yeah, I think so. Okay, so what's going to happen is we're going to start with, I'll come back to the picture in a moment. So we're going to start with the entities. So those are some vectors. The transformer will process that list of vectors in every step according to a rule I'll write down in a second to produce updated entities. So that's how the processing works in a transformer. Entities are updated over a range, over several steps. Yeah, okay. I can see the big green line in the world. I don't know how to get rid of that. That's unfortunate. Okay, so the formula is the following. So EI prime is equal to something called layer norm. I won't go into what that is. G theta of VI prime plus EI, where, and here's the important formula, VI prime is equal to some normalization factor, which I don't care about, j equals 1 to n, e to the qi kj, and then some phi v of ei. Okay, so this is another learned transformation. That's some z is some normalization factor that just makes those coefficients, the exponentials, add up to 1. Okay, so that's how you've just learned what a transformer is. So you can see that those dot products go in the exponent, and the ith v, so they're called value vectors, this value vector for the entity I receives updates, oh I'm sorry, that should be a j. So the ith entity receives updates from all the other entities, so all the other j's. The updates are of the form a linear combination of some transformed version of ej, so phi v of ej, with a weight which depends on these dot products. So you should think about that as messages being passed between the entities, perhaps. And the stronger that dot product is, the more a given entity I receives information from a given entity j. Okay, so we'll look at this example of three entities I, j, and k that I've drawn. Let's think about which receives strong updates. So if I think about the query for entity I, and then I look at the keys for entities j and k, well, clearly the query for I is in the same direction as the key for j, so there'll be a strong update for ei prime from ej. I guess I didn't specify here. This is some other learned transformation as well. Okay, so after the VI prime is produced, it's passed through another feed-forward network, and then it's added to the original EI. So what you're learning through this whole process is sort of the delta, right? So you learn, so this component here is how much you're going to change EI from one step to the next. Okay, so a strong message will be received from entity j to update entity I, but no message from entity k because the key is orthogonal to the query for entity I. And similarly, if you think about it, you'll see that there are strong updates in both directions there. Okay, so that's it. That's what a transformer is. Any questions at the moment? Okay, so now you know what a transformer is. Let me go back to the first board. And I'll tell you how to think about this maybe more algebraically, so in a style that Boole might have approved of, let's say. So I'll call this the Algebra of Attention. Okay, so the existence of a relation and j is a property of the product of this query for I and this key for j in what's called the Clifford algebra of that inner product space, right? Because if I take H, this inner product space, I can think of that as sitting inside what's called the Clifford algebra. I'll say a bit about this in a second. That has a multiplication, and this thing is a Z-graded algebra. So it has, every element can be written uniquely as a sum of things which are of degrees 0 through the dimension of H. And if I project onto the degree 0 part, which is just R, then the result of that chain of composites is that it sends a vector x tensor y. So you can think about that as an element of the Clifford algebra. You can multiply it, and the degree 0 part is just the dot product as a scalar. That's a property of the Clifford algebra, so maybe I'll just say briefly, in the Clifford algebra you introduce relations that say xy plus yx is equal to 2, the pairing of xy. So this has the result that the inner product is kind of one component of the product of x and y in the Clifford algebra. Okay. So you've seen how the dot product shows up in the rule for the transformer. Perhaps it's unnecessarily fancy to think about that as coming from a Clifford algebra, but what working in the Clifford algebra makes obvious is that, well, you don't need to restrict yourself to just relations involving two entities, because the rule for the transformer comes from thinking about products of queries and keys in the Clifford algebra in some tautological sense, because the dot product is part of the information of that product. But when you work in the Clifford algebra, it makes sense to form triple products. Let me just write down something like EI, EJ, EK rather than. So let me just elide these and just think about this here as being multiplication of the entities themselves. So you can think about ternary relations by taking higher products inside the Clifford algebra. So along with James Clift and James Walbridge, I worked on this in a paper we wrote for ICLR a couple of years ago. But a very similar construction showed up recently in the AlphaFold paper. I think it's completely independent, but they arrived at something similar without using the Clifford algebra, but the formulas are very similar. So the role of this triangular attention in AlphaFold is that it, given triples of residues in a protein, so these are these sort of building blocks of a protein, if there's a pair of bonds, well, there might be some connection between these two, which results in you wanting to reason about the triple as an unit rather than just reasoning about pairs. And so this triangular attention, or considering triples of entities and their interactions, is an important part of the AlphaFold architecture, which, as I said, is based on transformers, but now with this added feature. Okay, so the point I want to make is that transformers process learned representations of entities via geometric algebra, in a simple sense in the original architecture with dot products, and increasingly with more complicated expressions which make more use of the geometry of these queries and keys. And by doing so, they can play StarCraft, fold proteins, and do many other things. So I want to end with a kind of observation, which is that you'll find commonly expressed the belief that neural networks are good at perception, but not higher level tasks like abstract reasoning. And that might have been true 5 years ago, and arguably was still true about Alphago. But in the last few years, the AIs, so to speak, have entered the foothills of the mountain range of human reason. And I think the position that deep learning is incapable of reasoning is now no longer tenable. So we're in a position in 2021 where machines exceed humans in some forms of reasoning, often the forms that are kind of fairly shallow and not based on some systematic theory of what's going on, but incorporate a broad range of information. Maybe that constitutes what AlphaFold is doing, for instance. The true difficulty of the remaining forms of human reason where we exceed the machines is an open question. But I guess we're going to find out about that in the years to come. Okay, so thanks everyone. I'll finish there, and I hope we have a few minutes for questions. Oh, I haven't been monitoring the chat in case you were asking there. Sorry.
Thanks, Dan. I had a question.
Yep.
So I'm aware that like deep learning or AI has managed to destroy humans at like Go, chess, most games.
Yeah.
Is that also true for StarCraft 2 that I heard you mention? Because that's a bit more of like a real-time game that's a bit more intensive.
Yeah, I think that's a little bit more controversial. So they held a show match where they put Alpha Star against some of the best players in the world, and it defeated them, but maybe there was some argument that it was a little fragile, and if the experts had had enough time to practice against it, maybe it wouldn't have seemed so impressive. So I don't know what the final status of that is, but it's certainly, let's say, at the level of the best players in the world. Yeah.
Okay, cool.
I see some questions in the chat. Let me just read through those. No shout-outs to AlphaZero. Yeah.
Sorry, Dan, can I just carry on from what you just said, though?
Yep.
But wasn't there some advantage given to the machine? Didn't they could see the entire map or something? Isn't that true?
Yeah, I think there was in that show match that was the case, I think. Or at least,
yeah.
Well, no, I think there's a couple of things. One is that they couldn't see the entire map, but during training they could. So the value function was trained, being able to look at the entire map. At playtime they couldn't, but still, okay, the architecture also sees units as a list rather than actually having to perceive the pixels. So, and there's some detail about how cloaked units work that maybe arguably gives an advantage to the machine. I think there was subsequent, I mean, the actual paper was published something like a year after, maybe 6 months after the show match, and there were many refinements there which I think resolved most of those issues. So I think, yeah, I haven't paid attention to what sort of StarCraft experts think about it now, but my impression was that most of those early concerns were, just details that could be resolved.
Yeah.
I think when it was playing on ladder, it didn't have any of the advantages. They changed it. So a while after the show match, they changed it a bit and then put it on the public ladder just to play against people,
Right.
Anonymously, and it was not given any advantages during that. I think it was just playing as with the same information the human player would have.
Right. Yeah. You haven't been paying attention to the impact on the StarCraft community. I don't know if there's any StarCraft 2 players out there who can comment on. I mean,
I'm a big fan. That's why I asked.
Yeah, I played a lot of StarCraft 1, but I haven't paid attention to it recently.
I haven't played for a long time.
Because it certainly had I paid attention to its deep impact on the Go community. So I wonder, did Blizzard hand over millions of dollars so they could get the trained weights so they can just run it on the ladder nonstop? I don't know. No shout-outs to AlphaZero. Yeah, right. Well, it's a 30-minute talk, but definitely there are differences between AlphaGo and AlphaGo Zero and AlphaZero. Maybe your comment there is about the difference of the role of Markov chain, the tree search. I'm not sure. So there were subsequent versions of AlphaGo that made less use, sort of learned to basically do something like tree search, and which would lessen the critique that it isn't doing reasoning itself. But still, I think it's much clearer in the case of transformers that it's doing something like learning to process in steps that would seem to us something like reasoning on these entities. That's hard to argue when you look at how it actually works in practice and how those weights work in examples where you can understand what's going on. It's kind of hard to argue that something like reasoning isn't happening. How does the transformer get applied? Well, every time you do a Google search, I think it was 1 in 10 6 months ago, searches on Google homepage make use of a transformer to process your English language input or language input to see what semantically you mean, as opposed to just searching for the individual words separately. But machine translation is certainly all based on transformers now.